We're going to solve on this video some exponential equations that are able to be, everything can be converted to a common base. That is not true for every exponential equation. Sometimes, as we'll see later in the term, we're going to need to go ahead and convert some exponential equations to logs to be able to solve them. But in this particular case, I think we could re-represent each of these equations that we're going to solve with every term having the same base. And that's going to allow us to use some of the rules of exponents to solve this. So I don't know how obvious this is, but this problem, I'm going to write it again because it's really, its notation is this whole thing is the power. So we're really saying 2 raised to the 1 plus 2x power is equal to 32. So as we're going to work through log and exponential equations, we're going to see that one option is to take a look at an exponential equation and see if you could get like bases. This problem you can, because 32 happens to be 2 to the 5th power. So it's one of the first things you try. One of our other tools will be eventually to go and convert problems to logs. This problem actually can be solved with logs, but it's probably, when we can convert to a common base, a little faster. Watch what happens here. This problem becomes, I'll just start writing across here. This equation becomes 2 raised to the 1 plus 2x is equal to 2 to the 5th power. And it turns out when we have like bases like this, one of the rules that we're going to use when it comes to exponentials is, generally speaking, the rule is this. If you could get an equation converted where you have like bases on both sides, like that, in general, a to the v equals a to the u, then we can say that v is equal to u. We could just set their exponents equal to each other. And right here is that case. So we could just simply say, because of this, a to the v equals a to the u, we could just say that 1 plus 2x is equal to 5. And we could solve that little equation, which I'm going to do right here. I'll subtract 1 from both sides and divide by 2. And the exponent that would cause this equation to work would be 2. If we took a look over here, it would mean that if I put 2 in there, I'd get 1 plus 2 times 2 is 5, and 2 to the 5th is equal to 32. Okay, let's try it again. Now, it's really going to mean having to kind of dust off some of our knowledge of exponents, rules on exponents. Because in this case, to get this problem converted into an equation where I have like bases, I'd have to realize this. That first of all, 16 is 2 to the 4th power. So let's convert that to 4 raised to the minus x power is equal to 1. My mistake. I forgot this is a base of 4. I should have said instead of 2 to the 4th, a base of 4 would allow me to say that 16 is equal to 4 to the 2nd power, because I want like bases. But not only that, I've got to get this 4 to the 2nd to become an expression in the numerator. So we know, according to the rules of negative exponents, I could call this 4 to the negative 2nd. When you move an exponential expression upstairs and downstairs in a fraction, it changes the sign of its exponent to the opposite sign. So now my equation is 4 to the minus x is equal to 4 to the negative 2nd. And now I'm in the position to use this rule again. And because I have like bases, I could just simply say negative x is equal to negative 2. And therefore, my answer is x is equal to 2. And that answer happens to be D right here. And I could test it, of course. I could put, if you take a look here, if I checked it by putting 2 in there, I would get this. I would get 4 to the negative 2, which is really 1 over 4 to the 2nd, which is 1/16. Okay, last problem. So we're going to go ahead and take a look here with 2. Again, this exponent is a binomial expression of x squared minus 3 is equal to 64. So my hope is converting 64 to a base of 2. And it does turn out 2 to the 6th power is 64. And now I'm immediately in the position to go ahead and say that if I have a to the v is equal to a to the u, because of this right here, I'm going to be able to go ahead and say that x squared minus 3 is equal to 6, and I actually have a quadratic equation to solve. So I'm going to go ahead and say this. Well, only because the only variable in the problem is the squared term, instead of trying to bring everybody over and try to solve it by factoring of the quadratic formula, I think I'm going to move the 3 over, and I could solve this problem by the square root property and say the square root of both sides produces x equals plus or minus 3. Either positive 3 or negative 3 squared will give me 9, right? And, I could check that as well. So let's just do that. I mean, I didn't have much room up there, but this time I'm going to go ahead and write out the check to this. You don't have to check every answer, but let's see if we put, for example, negative 3 into the original problem. Let's see what would happen. I'd get 2 raised to the negative 3 squared minus 3. And the question is that equal to 64? Well, I would get, this is really 9, right? Negative 3 times negative 3. Negative 3 squared is 9. And is that equal to 64? Well, I have 2 to the 6th power, which we know, if you throw that in your calculator, is 64. And if negative 3 works, 3 should also. You'll end up right back at 9 minus 3 here.